Dr. Antônio Carlos, ele é membro do I3E desde 1995, é engenheiro eletricista pela UFRJ, formado em 95, recebeu os títulos de mestre e doutor pela COPPE UFRJ em 97 e 99, respectivamente. Durante 98 foi visitor escola na University of British Columbia, Canadá. De 2000 a 2002 trabalhou no Operador Nacional do Sistema Elétrico e desde então trabalha na UFRJ. Atualmente é professor associado do Departamento de Engenharia Elétrica da Escola Politécnica e no Programa de Engenharia Elétrica da COPPE UFRJ. Atua na área de modelagem de sistemas elétricos e na análise de transitório eletromagnético e sistema de energia elétrica.
Bom, doutor Antônio, temos 30 minutos aí para o senhor discorrer.
Bom dia a todos. O tema de hoje é a discussão de como, digamos, vascularizar a meia onda.
kV, and after that 800 kV. Professor Portela encouraged us to use physics to its limit. So instead of being limited to 6 gigawatts of the circular beams, we worked with circular and elliptical beams as well, reaching 8. And if we consider 12 conductors in elliptical beams, we reach 8 gigawatts. And for 800 kV, we can see there is an increase in gain of power. And the project of this line was done in detail, always thinking about the physical conditions. We always established the behavior using Maxwell equations, and from the Maxwell equations, we derived the circuit elements. For all configurations, our field on the soil never exceeded 9 kV per meter, within what we consider proper for the Brazilian standards. Just to demonstrate you the 800 kV beam, basically 4.8 gigawatts. The beam for the 1000 kV line positions in the tower and in red in the middle of the gap, reaching 8.6 gigawatts. The elliptical beam allows for a larger compactation and an elevation of the natural power. And this allows for us to generate larger powers, making our line a true transmission corridor. Here, the idea of working with one circular beam, and you can see that the elliptical beam, and the increase in relation to the conventional is considerable, but if we work with 3 elliptical phase, the power would be even greater. The electrical performance was very similar. So the values, there were differences in terms of values, but the over voltages were always within the limits. The voltage and the energization voltages were always within what was accepted, or even below 2 pu, because there's an unusual fact. These are very long lines, so the maneuver transients are damped. So, but if you consider the tower, the position of the surge arrestor, we would have a satisfactory performance as well. One thing that is important, why did we always look for this higher power? Because as I'm going to demonstrate after, the higher the nominal power for the secret, more margin I have to drain or inject power. We used to joke that we would like to make an autobahn of energy. So a large system with a large capacity for power, able to flow generation through long distance. Of course, there's always the problem, because since we are engineers, we need to think a little bit about costs. The unconventional lines with elliptical beams would be more expensive. But what we need to see is the price of this throughout the execution period of the line, and not on an immediate situation, thinking about a scenario of 30 years. Here we have basically the structure of the grid. We have an emission terminal, a receiving terminal, and a short line with 500 kV, an elevation of 500 to 1000 or 500 to 800 kV, my line of half wavelength, my tap, which can be shunt or series. And the idea was we're not going to limit to draining. Eventually, I'm going to allow for the injection of power in this large corridor. And I can have the AC tap both in shunt as in series. Always thinking, we always worked with lines with at least 2,500 to 2,700 kilometers. The first question was where to position the tap. So we scan the circuit with impedances where I can identify in this unitary length which are the nodal points, the main points where I need to connect my system. If I want to make a series connection, around the middle of the line would be the most proper place because it works with the minimum of power transmission. But if I want to connect it in shunt, I have the terminals as the most proper points of connection. This is the system that was assembled in further details. You can see that there's a small local load. In this circuit, we are considering the 8 gigawatts, 1,000 kV line. So this is a line without direct connections, without tap. The tap is connected here on the line. It can be in shunt or series. The series tap coming from a series transformer. You have power converters doing this work, and through this converting traffic with the tap in series, I can have a local generation feeding a local load. The idea here, just a little bit more details about the arrangement of the taps. My colleague tomorrow, Professor Marissa Reid, is going to give more details about this because tap cannot only be used to drain energy but also to control the flow. So we have tap in there in shunt, which would be the conventional one, shunt transformer, my converter, and the traffic of connection with the system. But the tap series always comes from a series transformer. The topology of converters is basically the same. Simulations indicated that we have a theoretical limit between 1/8 of the characteristic power. This is why it's interesting to work with high characteristic powers. On that line of 8 gigawatts, I could drain or inject 1 gigawatt. So if I had, the only problem is that initially the line needs to open close to the PC. So if I'm injecting 1 gigawatt, my generation cannot load the line with one PC. And the connection point, they are going to have to stay within the characteristic power. The results inducted that the tap shunt can reach up to 1/6 of the length of the circuit, considering this is a half wavelength circuit with 2,500 kilometers. This gives us a certain freedom. Tap series, although it is ideal for the middle of the line, we have to remember, since we are working with two lines, in case of loss of one of them, there will be the whole transport will happen through here. This would cause an increase in voltage that would theoretically go to 2. But the fact that we worked in this system representing the corona effect, we can see that the corona effect drains a lot of this over voltage, getting up to 1.7, 1.6, depending on the characteristics of the circuit. With that, we would have to stay basically up to 200 kilometers from the middle to avoid this middle point, which is a point where your line needs to be over isolated in case you're working with two circuits. There's always the issue of the increase of the characteristic power with price, because now I'm adding converters, so I'm going to raise the cost. These are expensive devices that require additional substations and controls. As an example, that line of 8.6 gigawatts and the event. So I initiate the tap and I drain energy from the tap as well as inject energy through the tap. And this is all a result. All these values were calculated with coming from the circuit. This was all modeled on PSCAD, trying to reproduce the behavior of the circuit. And we notice that the load remains unaltered. The same thing for its reactive power. Then you say, oh, I do not want to work with converters. I do not want to work with power electronic. So we would have the possibility of doing such as ELETRONORTE has done to cross the problem with this case is that there is a limit to around 8% of the characteristic power that we could drain from this circuit. Since my surge arrestor wire is a dual phase system, I'm going to need a substation or using a capacitor bank to feed the transformer and then have my three-phase system, or eventually having my own converter. Then I will get a little bit more than 8%, so this converter can generate the three phases. This converter would be exactly the same one as the one from the tap shunt. Another idea would be not using just one drain point or one injection point. I'm going to work with several injections. So the idea, if it's certain that I have something about 2,500 kilometers between circuits, anything extra can be connected, or let's say I would have several short lines, even with half wavelength characteristic, to spread my system. I could even have the idea of multiple inputs and outputs, and this is where the half wavelength plus becomes that transmission hub. It's going to be my main corridor connecting all the circuits. Of course, as I said before, this is an alternative to the use of converters. This is the basic idea. For example, this is the circuit working with 2510 is just to make sure that we are going a little bit beyond the half wavelength. Then I would have several connections covering the different loads in the circuit. The first question is, what is the minimal length and the maximum length of this additional branch? And what is the ideal rate for this circuit? The idea is that the theoretical limit would be close to 250 kilometers, because there would be the problem of the voltage at my connection point that I'm calling this V0. Eventually it's going to repeat here, but with 180 degrees behind. What I allow from it is going to determine the behavior of the half wavelength. If I allowed for eventually shorter voltages, I could have longer branches. The determination of the number of branches, for this we conducted this arrangement. We did something similar to the load flow of distribution when you have large radio systems, where I have the relation between the connection point and the several drainage points, as long as my connection point is single. This brings me to a system that is basically of this sort, where the voltage in my connection point of the input is single, and I can vary the voltages on the several load points. This system is a rectangular system. It is easily solved by QR. And we notice that when above 4 branches, the system becomes poorly conditioned. And the fact is that systems that start to escape physics tend to be poorly conditioned. We always worked with this idea of 4 branches, and then we limited it to 3 branches, because this possibility of spreading the half wavelength plus. The first case with the elliptical beam 800 kV line delivering PC, a main circuit with 2,510 kilometers. The circuit was modeled in EMTP. And we noticed that it's necessary to establish some procedures. It's not just assembling the system, because when we're transforming the half wave in a system with multiple terminations, there are going to need some operating criteria. There are 2 possible strategies for energization. I energize the main circuit and then one of the branches, or I energize the main circuit, and then after that I start to energize each branch. The requests are going to be different, and I have different efforts both in terms of the circuit breakers and the surge arresters. It's important that this transformer feeding the system is going to have to be designed together with the line for the demands that the line has, because as we have in the system, some transformers need to be energized together with the line because the line causes a resonance, then it cannot be energized. So you need to be careful with the transformer so the transformer is proper. So the transformer project needs to be in a way that is not affected by the behavior of the line. These are some results for the load divisions considering different lengths. We have always kept a limit, so you can see that there are compositions where you have branches of different lengths. Thinking about Brazil, it's very difficult to have branches with exactly the same length, but we have always observed that I need to have a division close to an equal division between loads, or a coordinated control between loads. If one load varies more than the other, it was necessary to perform some control actions. It's important to remember that in Brazil, the half wavelength plus would have possibly two connection points, one in the emission terminal and the other in the receiving terminal, due to how the system is organized. So possibly we'd have that 180-degree transformer being necessary. With more branches, we would have smaller 180 degrees transformers that would be cheaper, of course. This order is something that cannot be changed. Once you energize the first branch, you get the load, and then you energize the second one. The sequence of loads will always have to be very well coordinated to avoid overvoltages. In configuration number 2, we have the idea of the hub. So I'm going to have several different inputs, different emission terminals and different receiving terminals. The idea is that for one of these terminals always going to be connected to the line and others coming. You notice that in the end it's basically the same idea of the tap shunt. This came from the idea of the tap shunt. So instead of having a tap draining the energy, I have a system that is injecting or draining energy at this connection point. Here, since we consider a certain length here, it would be possible to limit this to smaller distance of my main circuit. This is the configuration number 2, where we start to establish the limits for the branches. This situation of the emission branch and the receiving branch, when they are smaller than 125 kilometers, I can have the other circuits delivering percentages of the characteristic power. Of course, that the idea is fixated from this point on until here. This needs the minimal criteria, the minimal conditions need to be established for what would be a line, half wavelength line. Here, the idea is I fixated one and connected the other points. So in this study, we allowed that if once you connect here, from this point on you do the energization, and the others are going to be connected afterwards. The order of maneuver is something that I cannot escape. I'm always going to have to prioritize them because depending on them, the demands from the circuit breakers are going to be different. So I have the same conditions from configuration 1, but with the advantage that my main circuit could be a little bit shorter. This is something very simple, so you have an idea if this would be economically doable. Once we have the cost for the circuit, and these additional branches would have to be similar circuits to the original one. So I'm building a circuit of half wavelength with several additional branches. So I always need to think about the cost relation between my new system, because initially it's going to be how, if it's little or not, we're going to need a specific project to know the exact cost, because we need to know this is a scale economy. We did the project for the tower, for example. It's a Dynetic tower. It's going to be expensive, but it is expensive when you're going to do one. If you're going to do a tower every 500 meters in a circuit of 2,600 kilometers, this is something that can be negotiated and getting more reasonable prices. As conclusions, we also presented very briefly some alternatives that makes the half wavelength plus a solution that is more than just a point-to-point solution, allowing for me to increase my distribution of loads injected in the system. AC tap can help the flow of power, but we're going to talk about this tomorrow. My colleague is going to present this. Multi-terminal can be done as long as we use converters, tap series for close connections to the central area, and tap shunt for connections close to the extremities of the line. Solutions without converters would have the advantage of not being scary from the technological point of view. I'm using technology that I would already have to use in the development of the halfway length itself. Connection without surge would be the most obvious load system, and also the most limited one. We can also think about the idea of creating a half wave length. I think this is a very interesting idea. Our pride and joy would be our central connection point, where all the large generations and large roads are fed from this point. Of course, that when I do this, there will be an additional cost from the initial cost of your circuit, but I believe that the gains in reliability, safety would be much greater. And of course, that I also would like to thank. We cannot conduct research by ourselves. This work has been conducted by myself, my colleague, Professor Edson Watanabe, Professor Robson Diaz, Professor Mauricio Oredes are the most active person. And as a reminder that yesterday, it was the 3rd anniversary of Professor Portela's death, and we thank him very much for everything he represents and has represented in our lives. Thank you very much. Thank you very much, Professor Antônio Carlos. You were one of the few that respected the time limit. We all also like to thank you for the minutes we have gained. We're going to open for questions now and for the discussion about this topic. I'm Sergio from CPO. Regarding the restriction you mentioned about the draining or injectioning, I did not clearly understand what was the restriction. Was it due to over voltages? Yeah, over voltages, it's like this. The idea was we tested the value of the injection and analyzed the circuit until we reached a problem. If it's dynamic over voltage, transient over voltage throughout the circuit, there was always some type of criteria to indicate that there was a problem. So this 1/8 was what we could notice a safe point for us due to the uncertainties. And my second question would be, if the restriction in this case, the dynamic, if this could not be solved in the configuration where the extraction is done in the terminal of the line, if this could be solved with synchron. To tell you the truth, we never thought about the synchronous idea. Because they are expensive, and these are devices that, where everybody's thinking about static compensation. So we always had the idea of static compensation. It's because synchronous, it's sometimes used as a solution for the AC link, sorry, the continuous current link. Perhaps this could be, but we did not consider this, and I cannot do the math right now in my head.
For you. To the best of my knowledge, nowadays the DC transmission technology is a new scheme called multi-terminal DC transmission and connection. Okay, my question is: have you done some research to compare, in the economy aspects between the two? Because here, what you have proposed is multi-terminal for AC transmission, and nowadays the multi-terminal DC transmission now is available. Yeah. So I think
Para os níveis de potência, a gente está limitado. To nowadays technology, we are limited to the conventional power of HVDC. We cannot go to, for instance, there's the MMC, multi-level converter. Yeah. With this one, you cannot reach the high power level that we need for the systems. You still have to use thyristors, so you are still bound to the conventional technology. And there's one problem, at least in my point of view, for HVDC in Brazil, because you have the grounding electrode for HVDC, and in the Amazon is not that easy. Very shallow soil, and you have a large and wide levels of rock, and the earth potential goes way high, and with that you cannot deal with a monopole, single pole operation. Mm-hmm. So I guess it still is a technical challenge. I'm not that concerned about cost, because in academia, if we don't dare, who would, right? So cost is something that I keep my mind on that, but it's not something that I'm driven by.
Okay, thank you.
Antônio, parabéns pela sua apresentação. Eu acho que é uma grande motivação para uma grande vantagem para um sistema.
Throughout the line, it's always 1/8. So if we use the one with 6 gigawatts, this would be 1/8 of 6 gigawatts, a little bit below 1. And we can use more than 1 point. Thinking about a single drain, if we had several drains, then the sum of them would have to reach 1/8. 1/8 would be the theoretical limit we considered. Final question. When we think about the transmission coming from the Amazon, we do not have areas where we'd have large load concentrations. 100 megawatts would be a large load, as it is the city of Palmas, a very large city. So from then on, we always have small loads. So I think this limit of 1/8 is way above what we had. But we can also think on the other end, because you have to think about it's close to the ends. I agree with you when it's in the north, but we'll have to think about the south as well. And in the south, 1 gigawatt, there will be many. You're correct. I know, I'm trying. Well, I would like to thank Professor Antônio Carlos.